it's easier with the microphone. The second conference is an introduction to the fundamental concepts to AI. We are going to talk about machine learning, deep learning, Gen AI. Let me introduce Joanna and Ammar before they begin. So Dr. GIEMZA, Joanna, is a data science and AI specialist dedicated to transforming healthcare through data-driven innovation. With a master in mathematics and a PhD in genetics, genomics, and bioinformatics. She has contributed to fundamental research at King's College London and the Institut du Thorax in Nantes. And she's now focuses on harnessing real-world data at the Institute of Artificial Intelligence in Health in Reims. And the second speaker, Dr. Ammar HASAN, is a senior data scientist at the Institute of Artificial Intelligence in Health in Reims. He is an expert in machine learning, NLP, natural language processing, and AI for healthcare, with 14 years of experience in data science research and clinical AI innovation. So, Joanna, let's present your project.
Hello, everyone. I will tell you today about fundamental concepts of artificial intelligence. So I will explain what AI is, why it matters, and where it came from. So I will provide you all the necessary definitions, and here I will explain the subtle differences between AI, ML, machine learning, and DL, deep learning. So AI is the broadest term. It's a field, a scientific domain that aims to enable machines mimic the human behavior. Machine learning is a subset of AI. Machine learning encompasses techniques that uses statistical methods to enable machines improve with experience. And deep learning is a subset of machine learning, which focuses on algorithms with multi-layers of neural networks. So now narrow versus general artificial intelligence. So I have already many years of experience in the field, more than 10, and few years ago, when I was presenting what I do in life, that I do machine learning, artificial intelligence, it was not ringing a bell to most of the people. Now, since ChatGPT release 3 years ago, everyone knows about AI, but I am not sure everyone knows what is the realistic scope of current systems. So everything we will discuss today, and most medical, all medical AI, is narrow and artificial intelligence. So its capabilities are to perform a single task, and the current systems cannot carry out tasks outside of their designed functions. Tech leaders claim we are close to the artificial general intelligence, so that has capabilities, all human capabilities, including their emotional intellect and creativity. But the truth is that artificial general intelligence so far exists only in sci-fi movies or books. The story of artificial intelligence begins over 80 years ago with a simple but revolutionary question. Can a machine think? In 1943, McCullough and Pitts proposed the first mathematical model of a neuron. It was primitive, but it planted the idea that a thought could be formalized as a network of logical operation. Then, in 1950, Alan Turing reframed the question. Instead of asking what intelligence is, he asked whether we could recognize it, proposing the Turing test as a way to measure machine intelligence through conversation. 6 years later, in 1956, at the Dartmouth workshop, the term artificial intelligence was coined. That meeting brought together the founders of the field, McCarthy, Minsky, Shannon, convinced that intelligence could be mechanized. And finally, by the 1970s, these ideas led to the first real-world applications, expert systems. This was the age of symbolic AI, machines that didn't learn but reasoned explicitly through human knowledge. The example of the first medical expert system is MISIN, developed at Stanford University. It was a rule-based expert system diagnosing bacterial infections and recommending antibiotics, and it contained about 600 if-then rules based on expert physician knowledge. It was groundbreaking because it demonstrated that AI could reason like a specialist, and it introduced explainability. MISIN could justify each recommendation, and it inspired later systems in other domains, in oncology, cardiology, and intensive care. Symbolic systems had some limitations. They needed manual rule creation. Experts had to define thousands of these if-then rules manually. It lacked as well adaptability. It couldn't handle uncertainty or learn from new data. It was not learning, it was only following the logic. And lastly, it had a poor scalability. Each new medical condition required rewriting the rules. So after the first successes of symbolic AI, researchers hit the so-called AI winter. Progress slowed as systems became too rigid and costly to maintain. So the results were overpromised and the performance under-delivered, which reduced the funding. The failure of this rule-based AI revealed a need for systems that could learn patterns directly from data, leading to the rise of machine learning. So here is the timeline again with the major periods. Major periods of AI. So from programming knowledge from 1940s to 1970s to learning from examples. The machine learning revolution began in 1980s. So knowledge no longer programmed, it is learned from data. Machine learning relies on statistical inference and optimization. So here is a precise machine learning definition. A computer program is set to learn from experience E with respect to some class of tasks T and performance measure P. If its performance at task in T as measured by P improves with experience E. Very mathematical definition. But we have the trifecta of experience or data, task or model training, and the performance evaluation, the 3 pillars of machine learning. So now I will tell you how the machines learn from data based on these 3 pillars. As for data, data are the examples and often labels. So data features, it can be a measurable variable such as age or pixel intensity in an image. And labels is what we want to predict. For example, disease, type of cancer. And I would like to highlight that quantity and quality of data are crucial. Quantity, because ML algorithms are data hungry, and just like students that need many case studies to gain knowledge. And quality, because the rule garbage in, garbage out unfortunately applies. So let's move to the second pillar, model training. So model is basically a mathematical function linking features and labels trained with the help of loss function. Loss function measures the differences between predictions and the reality. And model training is a learning process where model parameters are optimized, adjusted to minimize loss. So there are three types of how machine learns, three ways. So unsupervised learning, supervised learning, and reinforcement learning. Unsupervised learning is basically we find the structure in unlabeled data. So yeah, it is the name of the machine learning where we have data without labels. Supervised learning occurs where we have data with labels. So we learn from labeled examples. For example, we predict a disease risk from patient data. And the last type is reinforcement learning, where we have a whole environment to interact with, states and action, and we learn by trial and error. Here I prepared for you the three simple classical ML examples, examples of ML techniques. So the first is linear regression, probably the simplest form of machine learning. So the computer learns a straight line that best fits the data. So if you plot points of, say, blood pressure versus age, the algorithm finds the line that minimizes the prediction error. It's like saying, given what I've seen, this is the trend. It's simple, transparent, and yeah, kind of mathematically elegant. And the second example is the decision tree. So instead of a mathematical formula, it learns a sequence of if-then decisions, very intuitive for us humans. For instance, if the temperature is high and the cough is present, suspect an infection. So it mirrors how doctors reason through choices, and the resulting model can actually be read like a flowchart. And the third example, I wanted to give you one example of unsupervised learning. So it's a K nearest neighbors, KNN. So when you give it a new data point, it simply looks at its closest neighbors in the training data and predicts the cluster assignment based on them. So in other words, show me the similar cases and I will guess accordingly. So this classical models remains foundational today. In particular, decision trees can be combined into ensembles with algorithms such as random forest and XGBoost. And I'm sure that Ammar will give you the project examples with this later in the talk. So back to this slide, the evaluation part. Evaluation, which means measuring performance on an unseen data. And a good model has a strong performance on unseen data. the patterns that it learned from the training data generalize on the new data. So a poor model does not generalize. It's like a student who memorizes past exams, but fails when the questions change. So to sum up this part, we start from data, build a model that learns patterns, and test if it generalizes, and repeat. It's an iterative process. And machine learning is all about finding a balance between learning from the past and performing well on the unknown future cases. So now there will be few technical slides. So please focus. One of the central challenges in machine learning is finding the right balance between the bias and variance. And this target diagram explains it well. So imagine each dartboard here represents the possible outcomes of a model predictions. And the bullseye is the trough. A model with high bias consistently misses the target. High bias, it consistently misses the targets. So the darts are clustered together, but far from the center. It's simple to capture the complexity of reality, like using a straight line to predict something linear. A model with high variance, the two here, they hit all over the place. Sometimes close, sometimes far. It's too sensitive to the training data and fails to generalize. What we want is low bias and low variance, darts tightly grouped around the bullseye. So that's the sweet spot where the model captures real patterns and isn't fooled by noise. And this trade-off between being too simple and too flexible is at the heart of every learning algorithm, from linear regression to deep learning networks. So now let's connect that idea of bias and variance to what happens as we make a model more complex. On this graph, the x-axis shows the model complexity, how flexible or powerful the model is, and the y-axis shows error. If a model is too simple, so low at the complexity level, it can't capture the structure in the data. So that's the underfitting region where the bias is high. So yeah, this is the bias relationship and the variance. So as we make the model more complex, the total training error here in black keeps going down because the model is learning to fit the data it sees. But after a certain point, it stops improving and starts to rise again. That's where overfitting begins. The model is memorizing noise instead of learning general patterns. So you see the line connecting points is very, very complex. The lowest point of the error curve, right in the middle on this graph, is what we call the optimal complexity. So that's the sweet spot where bias and variance are balanced. In practice, this is why we use validation data, not to make the model perfect on what it has seen, but to make it good at what it hasn't. A useful technique of validation is cross-validation. Instead of training the model once and testing it on a single held-out data set, we divide our data into several smaller parts called folds. Then we train the model multiple times, each time leaving one fold for testing and using the rest for training. Every fold gets a turn as the test set, and in the end, we average the results across across all the faults. Averaging gives us a more stable and fair estimate of how well the model will perform in real life. Cross-validation is especially valuable when the data is limited, like in many medical datasets. It is valuable because it allows us to create all the data for both, allows us to use all data for both training and testing, just not at the same time. So after these technical slides, let's go back to the historical context. Up to this point, models depended on us to define what mattered, the right features, the right descriptors. And around 2006, it changed. Machines began to learn their own representation of the world. That's the beginning of deep learning. Deep learning enabled AI systems to discover features directly from raw data, such as images, signals, or text. Why deep learning emerged and what changed? The three forces converge. More data, more computing powers, more GPUs, and finally, better algorithms. For example, the propagation improvement. So the neural networks revived after decades of dormancy. So now how deep learning works, I will not give you a formal definition. I will try to convey the intuition. So each layer extracts progressively higher level features. So in the input layer, we have pixels. Then in the next hidden layer, the model learns how what are the edges in the pictures. Then it distinguishes shapes, and lastly organs. And in the final layer, it is able to give a diagnosis, for example, tumor or no tumor. Deep learning enables the end-to-end learning. There is no manual feature engineering as previously in the classical machine learning. Once a neural network became powerful enough to learn complex representations, researchers started to adapt the structure to different types of data. And that's how we got these four major families of deep learning architectures. The first is the convolutional neural network, CNN, the workhorse of computer vision. So CNN learns from images by scanning small patches, convolutions, across the picture. So they can detect edges, shapes, textures, and ultimately recognize the whole structures. And that's why they are used a lot in medical imaging, from CT scans to pathology slides. The second architecture is the recurrent neural network, or RNN. So these models are designed for sequences. They remember what came before. RNNs process time-dependent data like the electrocardiogram signals. They capture temporal dependencies. They capture when as well as the what. The next type, autoencoders. Autoencoders learn to compress and reconstruct the data. You give them an input and they try to reproduce it after passing through a narrow bottleneck layer. That bottleneck forces the model to learn a compact representation, often used for dimensionality reduction. And finally, the transformer, the architecture behind modern language models. Transformers introduce the concept of attention. Instead of processing information sequentially, they look at relationships between all parts of the input at once. So they're the backbone of today's medical NLP, among others. And to sum up, each of these architectures represent a different way to learn structure from data: spatial, temporal, latent, or relational. And together they form the foundation of deep learning today. The last technical term for me today is the transfer learning, reusing the learned knowledge. So training a deep neural network from scratch requires enormous amounts of data and computing, something we rarely have in medicine. Instead, we use transfer learning. We take a model that's already been trained on a large general dataset and adapt it to a new specific task. For example, a CNN trained on millions of everyday images can already recognize basic visual patterns. It can recognize edges, textures, shapes. And when we reuse it for radiology or histopathology, it already knows the visual language. We just need to teach it medical vocabulary. This approach saves time, improves accuracy, and works remarkably well even with small datasets. In essence, transfer learning lets AI start as an experienced learner, not as a blank state. And there are two main strategies for transfer learning: the feature extraction and fine-tuning. So in feature extraction, we freeze the pre-trained network and only use it as a feature extractor. It converts our images or signals into meaningful numerical patterns, and then we train a simple classifier on the top. So this is our old pre-trained model, and we only train a simple classifier at the top on the new data. The second type of transfer learning is fine-tuning. And in this case, we allow part or even all of the pre-trained network to continue learning on our new datasets. So it's possible that all the parameters of the pre-trained model will be adjusted to the new data. We adjust its internal representations slightly to fit the new task. Feature extraction is faster and safer when we have little data, and fine-tuning gives better performance when we have enough data to carefully adapt the model. So in short, we can either reuse the knowledge through feature extraction or refine it through fine-tuning for our own domain. So this is my last slide to sum up. So artificial intelligence, we know many of its application in our daily life, autonomous driving system, the algorithm underlying the social media, the navigation, translation of foreign languages. There are also numerous applications of AI in medicine, for example, the deep learning algorithms for electrocardiogram signal analysis, the many AI applications in medical imaging, for example. So now I will give the microphone to Ammar, who will present you some examples of AI in medicine projects in our institute. And in the time of transition, I can take one or two questions. And thank you very much for being here.
Yes, exactly. As Joanna said, we are going to answer a few questions, few short questions, if you have any. We see that we didn't have any questions so far, but just to remind you, during the presentation.
Thank you, Joanna.
Oh, we have one question, Joanna, if you want to answer it.
Okay.
So the question is it possible to explain what reinforcement learning is?
Oh, I will take it after Ammar's talk. So I will focus.
Okay, so we will answer it in a few minutes. Thank you, Leia.
Thank you, Joanna, and good afternoon, everyone, and I thank you for joining these sessions. My name again is Ammar HASAN, and I'm a senior data scientist at the Institute of Artificial Intelligence in Health at Ghans University Hospitals. Today, I'm going to walk you through how we are transforming raw clinical data into practical, safety-oriented tools that support clinicians in real times. So our work focuses on leveraging artificial intelligence, particularly machine learning, NLP, deep learning, and all of this kind of tools. We use all of these tools for early risk detection, support decision making, and optimize clinical resource, and of course, ultimately to improve patient outcomes and healthcare efficiency. Today, I'm going to present two major projects as examples. The first uses machine learning to predict or to proactively identify patient at high risk of medication error. And the second project uses natural language processing to generate real-time virality scores directly from unstructured clinical notes. So these two topics highlight how AI can move healthcare from reactive models to a more proactive and preventive one. So let's begin. As you know, modern hospitals generate massive amount of clinical data, structured and unstructured. So clinicians must navigate all of this type of data. So for examples, electronic health records, clinical notes, lab result, imaging result, medication list, and continuous monitoring. So, but despite this abundance of data, critical clinical signals can remain hidden. Yeah, that is definitely clear because you have all of these enumerous on massive number of amount of data. So the critical signals, uh, clinical signals will be hidden and under all of this kind of data. So important, for example, important indicators of risk, whether medication discrepancies or early signs of frailty of patient often hide in a place where uh, clinicians don't have the times or the bandwidth to manually search. So our mission at the Institute is to turn these overwhelming volumes of data into clear, actionable intelligence that help or that support clinician intervene earlier and prevent harms. So instead of relying on retrospective informations or manual detections, we aim to build tool that proactively show the right signals at the right times. The first project is about a machine learning tool to develop a machine learning tool to identify a patient at high risk of medication error. So the first project addresses a major patient safety challenge, medication errors. This error occur frequently during hospital admissions and are recognized as one of the leading cause of preventable harm in healthcare. The gold standard, the gold standard uh, methods to reduce this medication error is called medication reconciliations, and this kind of procedure usually uh, leading or performed by a clinician pharmacist. but pharmacists are a scarce resource, a limited resource, and not every patient can be seen immediately. So the central questions we asked was, can we use machine learning to predict which patients are most likely to experience a medication errors, and help pharmacists focus on those cases first. So this project explored how structured hospitals data can be converted into a predictive risk scores that support safer and uh, more efficient care. This slide just to give you image of medication error outcome and burden in USA and Europe. It's costly a lot in terms of death. In Europe, in USA, we have like between 7,000 and 10,000 deaths annually directly attributed to medication errors, while in Europe also we have several thousand of preventable deaths annually, and it costs a lot in both of the places. In USA, it costs around 20 to 40 billions dollars annually, while in Europe it's almost the same, between 20 and 30 billion euro annually economic burdens. So let me give you also a bit more context about medications errors, which is remain one of the top preventable causes of patient harm worldwide. Medication reconciliations. The good thing with the medication reconciliation is that it can, which is performed by pharmacists, can reduce this medication error by up to 66%. But in practice, as we know, as we said before, this the number of pharmacists is a scarce resource, is a limitation resource. So pharmacists cannot see every patient at admission. So simply due to time, due to time and staffing limitation, normally a normal um, medication reconciliations take at least 1 hour for each patient. In hospital like Gans University hospitals, we have uh, plus more than 100,000 every year patient admitted in different department of hospitals. So that means we have like between 200 and 300 patients every day admitted at the hospital. So impossible for pharmacists to make medication reconciliation for every patient. So what we did actually here, we take like randomly the patient for chooses for patient for medication reconciliations is chooses randomly. So our goal actually is to build AI driving tools that identify the patient who are most likely to have a medication discrepancies. Instead of reactive models where errors are discovered after they happen, we aim for models where risk is flagged before harm occurs. So this kind of system will allow the pharmacist to focus their expertise where it's needed most. So to build these predictive models, we use the electronic health records of Gans University hospitals. We start from data set including like about 7,200 patients who underwent medication reconciliations between 2017 and 2023. Each record for each patient contained 52 clinical and administrative variables, and we train 4 models, machine learning models. We start with 4 models to see which one is produce the best results. So we choose logistic recognitions. This is classical machine learning models, superfactor machines, and extreme gradient boost models, and footing classifiers. The idea wasn't to just to achieve a good accuracy, but to create a risk scores that is clinically useful, interpretable, and feasible to integrate into hospital workflow. Here is the result from our models. Our base model was like the voting classifiers among the four model we use. The voting classifier is produce the best results. Honestly, there is not big difference, but the fitting classifier is giving the best, produce robust performance metrics for recalls. Metric is about 75%. If one score about 70% also, but we are not care much about this performance. We care about in the real case, but more importantly, actually, in real world perspective evaluations, we have been testing these models in a real world. So we find that our model demonstrated 113% improvement in compared to the existing method. So it identifying patient at risk with improvement 113% comparing to the existing method in the hospitals. So the current method, methods used for a long time in hospitals, capturing about 21% of patients at high risk, while our models, AI models, identify 45% of those patients. So you can see that more than twice as many patients we are truly at risk can be flagged using earlier, and prioritized for pharmacist review. So since we have limited resources of pharmacists, so with this kind of tools, the pharmacists can target their expertise to only those patients they are really in need for medication reconciliations. And actually, this result is really a significant leap forward in proactive patient safety. Clinical impact and future integration. So now that we have seen how the models perform, let's talk about what is means in terms of clinical practice. First, these IA tools, improve patient safety by enabling pharmacists to intervene earlier, focusing their attentions on patients with the highest risk of medication error. Second, it helps optimize limited resources. Since we have limited resources, so that one we only targeted this limited resources to those really in need. So instead of relying on manual systems, on manual selections or first come first serves approach, the pharmacist can work in a more targeted data-driven way. The third point, currently these tools we have been developed already under the prospective evaluations, meaning it's already integrated into the clinical workflow. So it's almost like for more than 7 months already in the field or integrated in the workflow of the clinicians. And every month we have been retraining the models with the new data, and the result, this is the first result we have seen 130% improvement than the existing method, but now the result is already improved since we improved the training data. The models is giving us better result and better results. This kind of integrations, so because is our goals at the end is to integrate these tools into the electrical health record systems as a decision support module. Now we move to the project 2, which is about automating frailty scores from unstructured medical records. The second project takes us into a different but equally important domain, frailty assessment in hospitalized elderly or geriatric patient. Why frailty assessment is critical yet difficult? Frailty is one of the strongest predictors of fall, disability, length of stay, complication, readmissions, and even mortality. However, hospital frailty risk score is usually based on ICD-10 codes. By the way, the ICD-10 codes, for those not in the medical domain, is a international classifications code disease. So this code is given to each disorders or symptoms for inside the clinical note of the patient. So for example, diabetes 2 is has the ICD code E11. So for each codes, they have for each disease they have a unique codes. Since the hospital frailty risk scores is based on ICD code, the problem with these things, which this kind of codes, which not be available until the month after the patient is discharged. So during these periods, after the discharge of the patient, we cannot know the frailty scores of this patient. So this means real-time identifications of a frail patient is not always possible, and opportunities for early intervention can be missed. Critical notes contain rich, detailed information about patient diagnostics, functional status, mobility, conjunctive issues, and social situations. So as you see, is really a rich source of information about the patients, about the also about the situation of the patients. They include phrases like inside the clinical note. They include phrases like need help for walking, for bathing, for going to the toilet. They also include phrases like difficulty for eating, or they also indicate this patient lives alone with limited support. So all of these things, it can be used to calculate the frailty of this patient. These details are critical for understanding frailty, but they are unstructured and often hidden in a long text entries. So our goal was to extract these informations automatically and translate it into a frailty scores that clinicians can use at the moment of admission rather than days later. This support earlier mobilizations, better discharge planning, and more personal geriatric care. So to build these systems, we started with a data set of 400 clinical notes from patients aged 65 and older at two hospitals in France, Reims and Tours hospitals. So first, we clean and standardize the notes using a model called OLAMA, so LLM model, to ensure the text was ready for downstream analysis. Second, two medical doctors annotate each note, providing the ICD codes that describe medical disorders and functional or social problem, and also provide a 3-level frailty score for each patient. So the frailty score is giving low, moderate, or high for each patient. This expert annotated dataset serve as the gold standard for evaluations. We will be this 400 notes it will be used at the end for validate our NLP models. So it will allow us to compare different NLP models we have been used in this project and ensure that the final systems would align with the real clinical judgment, not just a mathematical pattern. So we deployed a multi-pronged strategy to identify ICD code from text. So because we have some kind of limitation for every models of NLP models. So for that, we leveraging multiple models for maximize uh, the accuracy. So our approach combined like several complementary NLP strategies. First, we use Dr. BERT and UMLS, Unified Modified Medical Language Systems, models to detect medical disorder embedded in the text. So we have to first detect the problems, and then we have to predict the code for each problem. So for detecting the problem, we use Dr. BERT and UMLS models to detect problems or medical disorders embedded in the text. For example, identifying conditions like malnutrition, dementia, or mobility limitations. Second, we fine-tuning Camembert and Alibert. By the way, we are working in the French clinical notes. So we use this Camembert and Alibert because it already trained on medical or a very big uh, medicals, biomedicals documents. So we use them, and we fine tune Camembert Alibert on a large data set, 130,000 AI generated sentence. So it's not a real data for fine tuning, but we generate using the ChatGPT. So to fine tuning the models, it's only for just because, as you know, this scores of frailty scores it doesn't use all of the ICD codes. Uh, it's only use 109 codes. So we have to fine tuning uh, the Camembert and Alibert based on the 109 codes. Third, we mapped UMLS concept to ICD code. The good thing with UMLS is can detect the medical disorders, and also during detection, this kind of disorder is giving us CUE, so concept unified identification. So we can connect to the ICD code directly. We don't need to predict. If you use MLS, you don't need to predict the ICD codes. You just use some kind of model of ontology to connect the ICD code, the medical problem with the ICD codes. So finally, so now we have like two models to detect the problems, UMLS and Dr. Bert, and we have three models to predict the code, ICD code. We have Camembert, Alibert, and UMLS. So we fuse all of these codes coming from the three models to um, to combine one set of codes, and we find that uh, the multi-model fusion approach gives us a much higher accuracy than any single model alone. That is because each model has a limitation. So when we use this kind of fusion between more than one models, because each model is looking from different viewpoint for the data, so it's giving you some kind of feedback or results. So if we combine all of these things, it's giving us better results. As you can see in the first project, we're using voting classifiers. Voting classifier because it's using more than one models to give the predictions or the classifications. So also here we use more than one NLP models to give the final ICD code, which will be used to compute or calculate the frailty scores. The result was highly encouraging. The automated frailty score produced by our system matched or in agreement with the expert physician's assessment in 90%. So 90% of our frailty score generated by our system is same as the expert, physician expert. So, and the most important part, even with those 10%, we are not in agreement. Our models like make wrong scores. It was a good thing actually, because it's in this 10% of cases where the model was wrong, we can considering the discrepancies was clinically safe. What means that? What that means when the model, when the patient has like low scores in reality, and this score is given by the expert, our model giving that patient moderate. So it's considered like clinically safe. So instead, when it was wrong, it tend to classify low risk patient as moderate. So that is a much safer error pattern in a clinical setting. So the level of agreement, this level of agreement demonstrate that NLP can reliably synthesis complex clinical informations from unstructured text, providing a real frailty scores that support early intervention and improve patient management. Let's talk about what this means for real-world geriatric care. Throughout this project, we successfully developed a fully automated NLP pipeline capable of producing a validated frailty score directly from clinical notes. We say validated frailty score because we compare the score generated by our NLP models with the scores given by the expert physicians. So with the 90% accuracy against expert, this tools has the potential to provide a real-time risk assessment as soon as the patient arrives. This is a major shift. Instead of waiting for ICD coding at discharge, care teams can identify frail patient early enough to mobilize geriatric teams, initiate a physiotherapy sonars, or adjust nutrition plan, and plan safer, more personalized discharge strategies. So in other words, we are moving from post-hoc documentation to a proactive clinical actions. Augmented clinical expert with AI. Oh, this is the one before the last slides. So as you can see, both projects share the same philosophy. We are not replacing clinicians. We are augmenting their experts. Project 1 uses structured data to optimize pharmacist effort. Project 2 uses unstructured text to uncover hidden geriatric risk. So these two examples illustrate showing the broader vision of our institute. AI systems that act as clinical co-pilots, quietly running in the background, analyzing data streams, and showing the insight that matter most. The goal is to help clinicians make faster, safer, more informal decisions supported by evidence generated directly from their own data. So thank you very much for your attentions, and I hope this presentation has given you a sense of how data, when processed intelligently, can be transformed into meaningful, actionable tools that enhance patient safety and improve clinical care. At the Institute of Artificial Intelligence, in health. We believe that the futures of medicines lies in this close partnership between human expert and advanced computational methods. So I would be very happy to discuss any aspect of this project, and I welcome your thought, questions, and idea.
Well, thank you, Ammar, for your
So this is the
presentation.
last, I think, the last slides. If you are interested in collaboration, so guys, if you want to reach me anytime, that is my email. And if you are interested in collaboration, data partnership, or implementation similar tool in your hospitals or research centers, feel free to reach out. And thank you again for your attending. And I know open the floor for question and answer session.
Yes, exactly. Now we're going to get to our Q&A section. So thank you, Ammar, for your presentation. And also thank you, Joanna. I see that we already had a few questions. So I think that this one is for Joanna. It's by Leia, who asks, is it possible to explain what reinforcement learning is?
Yes. Sandra, just a question for you. Can you perhaps show
Yeah,
us?
sure.
I have problems to see the question and answer panel. So if you can just project it. And yes, it's a very good question because I went very quickly in my presentation about it. So there was one slide when I was presenting the three ways that machine learn, the unsupervised learning, when we have unlabeled data and we look at their patterns, the supervised learning, when we have labeled data, so we kind of want to make predictions based on our examples and labels. And there was the third, the reinforcement learning, when I told you the input in this kind of learning is the whole environment, and the model is it's not as simple as mathematical link between the input, the examples and labels. Yet this definition was the most accurate for the supervised learning paradigm, and of course the reinforcement learning rest it was about mysterious. So it's a completely different paradigm. So a model in the reinforcement learning concept context is an agent. So an agent that it has its states, it takes an action and observes what happens after this action, and then receives either a reward or a penalty, and it adjusts the model parameters to optimize its strategy. So the final output is an optimal strategy, and he does it to maximize the total reward. So it's a bit like, training a pet, a dog. So if the model does the right thing, the pet gets a treat, and if it does the wrong thing, it doesn't get a treat. So, in real time, for example, if you use ChatGPT, sometimes it shows you the two options of the answer, and you're supposed to choose the preferred one. That's why they do it, because there is a part of reinforcement learning that in which they want to optimize the performance of ChatGPT, and we users are the environment that gives the reward for that chooses which is the preferred response. Another example is many years ago already, it was there were artificial intelligence systems for games like Alpha for Alpha. What was it called? I forget. Alpha 1, or the first AI that played very well chess, and AlphaGo that managed to beat the best Go world player. This kind of algorithm has a strong reinforcement learning component. Me personally, I'm totally not a specialist, because in our context, medical AI, it's not something we do first, because imagine, first we cannot really add additional burden to doctors to help us choose that, yeah, perhaps this prediction works better, and the other we cannot really permit to take more of their time to give us the rewards, or we cannot really also give this environment for, that perhaps a model can make a mistake, but he will learn from its mistake. We don't have this environment. It's also a lot used a lot in robotics. So imagine there is a robot in a maze, and if it hits a wall, it gets a punition, a negative reward. Oh, yeah, can we say negative reward? But yeah, a punition, maybe it's better. And if it advances to the exit of the maze, it's a positive reward, and eventually the robot will learn the optimal path. But maybe so. I prefer not to ask the follow-up question of someone else, what are the main algorithms used in reinforcement learning, because it's not something I do a lot. So if it's okay for this clarification about reinforcement learning, I will perhaps pass to the second question.
Yes, so Noor, we will follow up afterwards for your first question. Or I don't know if maybe Ammar has an
There
answer
was
to
one question,
one.
I already make a link because someone asked in the chat about what are the main algorithms.
Yes.
As I'm not an expert, I prefer not to discuss. Of course, there are the main classes, but
Well,
yeah.
there's no trouble. We can always
Yeah,
follow up
but there is
afterward.
the next question in the chat from the same person. I will be happy to take it. In which situation we should use traditional machine learning algorithms instead of deep learning model, and what factors help determine the most suitable approach. So it's a very good question. First, kind of a rule of thumb. If for a problem we have, there is a traditional machine learning algorithm that has a comparable performance, I would say we should stick to that classical machine learning because the advantages are less computational resources that are used, and very often better interpretability. But of course, it's just philosophically, do it as simple as possible, but not simpler. So we have to identify the situations that where the classical machine learning algorithms are not, just as simpler than possible. So, and less philosophically and more concretely, for a data that are, tabular data, the Excel spreadsheet, for example, of tabular data. In my opinion, classical machine learning algorithms such as XGBoost are still a state-of-the-art algorithm for that kind of data. And the deep learning models are better for structured data such as images or text. Yeah.
So next, I think we have a few questions for you, Ammar.
Yes,
I hope that
can
you
I
see the
see that?
questions.
Can
Yes,
you
go
show me the
ahead.
questions?
Yes. So the first one, so it's going to be shared on the screen. The first one is, what was the threshold that
Threshold,
gave?
okay, that
Yeah,
give 65% of
exactly.
recalls.
Yes.
Actually, this is based on the validation result, the validation data. We have been divided our data and using this kind of cross validation. So, and also we have some kind of external text, external data using for evaluate the models. So it's based on that. So, and the AUC, the area under curve, it was also 75. This work actually have been published. You can find it, the paper under the same names. I don't know if I can show you, if I can partage or sharing the, yes, I can share the, okay, let's make this to machine.
Yes, if someone else also has a question, in the meantime, I remind you that there is the Q&A section. If you want Ammar or Joanna to clarify a subject, don't hesitate.
I don't know if it's been seen or not.
Yes,
I
we can see your
partage,
screen. Yes.
but I didn't see it in my sites. I don't know why.
We see a PDF with a prediction tool.
Yeah, but I didn't see it. How we can,
No worries.
okay. That is actually everything is about the project. It was you can find there. So we use this kind of recall, but as we mentioned, we are not really considering this score much because we discuss like in terms of retrospective result. But in the reality, we have these good things. We have 113 improvement in terms of finding compared to the existing tools in terms of finding patient at high risk. So we have like, if we use this, we put our models to choose patient for medication reconciliations. And we also ask another groups of pharmacists to doing their traditional work as so like I think we choose we select 110 patient by models, AI models, and 110,000 by using a normal uh, tools for choosing the patient, and it was like randomly. So we find at the end, those patient choosing by existing tools is 100 is 21% of the patient has been uh, uh, founding with medication errors, at least one medication errors, and for you, the patient, the group of patient by our AI models, we find more 45%. So 45% of the patient was have medication errors, at least one medication errors. So at the end, you can see that we have our models find more than twice patient compared to the existing tools. For the second one, we, yes, Olama is not a LLM, but is a way to access models. So we use GPT OS 20p. So that is fast and can be used directly using the Olama. And this, we develop a prompt to just to clean the as you I to clean the document and to restructure the document. I hope this is clear for all of the questions. Yeah, for the ulama, we already use it with the ChatGPT OS 20p, but I think you can use another's, but we find that is okay for us. And for the 130,000 sentence generated, we use ChatGPT to generate this kind of things because we to have something similar reals, you need to hiring doctors or expert to annotate. So it's not easy to annotate this amount of data for fine tuning. So we choose to generate by ChatGPT for fine tuning the Camembert and Alibert models.
Okay, thank you,
Okay,
Ammar.
that's all. Yeah.
So that brings us to the end of today's session, I think, besides if someone else has a question. So I'm going to let Emily close the webinar.